So good afternoon, everyone. We meet again. So mine is the last but one presentation. Of course, technically, I think the last presentation, Dean R&D would talk about more aspects of the administrative things also. So what I have done is I have tried to keep focus on things which we've maybe, of direct interest, especially in Industry 4.0. So I have a very large group and I have been working in various areas for 25 years. And what I'll be talking about is digital transformation, a journey from digitization to digitalization. Today, almost everywhere you have data available. Any process, any equipment, anything which you do, you have data available. SCADA systems are very common. You can't make a manufacturing process without a SCADA system. But the question is, what do you do with that data? Is that data a cost center for you? Is it a profit center for you? You have large data centers where you are storing that data. That becomes a cost center. If that data starts working for you, that's when it really becomes a profit center. So it's like your money. You put it in your own house. It doesn't earn you anything. You invest it. It starts making money for you. So that's where we look at data in a very different manner. I'll very quickly talk to you from where I'm coming because it's important to understand the perspective. So I'm a metallurgical engineer from IIT Kanpur. I did my metallurgical engineering more than 30 years back. Then I moved on to do my master's, PhD. I worked in a NASA project where I did a lot of image processing, image analytics, and that's where I really got into image processing and aspects of digital signal processing. Came back briefly with National Aerospace Lab, went back to IIT Kanpur, became a faculty in metallurgical engineering, went back to US, my alma mater at Georgia Tech for a year over there. Decided to look into corporate R&D, left IIT Kanpur, went to General Motors, joined Detroit. Big stuff. Automotive was not doing so great, but that was the time when I switched to General Motors. Stayed there for a while. Then they started their center in India, so moved back to India in their tech center in Bangalore. Was there for a while. Later, decided the challenge was over. Came back to academia, but this time to IIT Bombay and to not metallurgy, but mechanical engineering. And about 7-8 years back, I started a graduate elective in machine learning, primarily driven by image processing, which I had been doing throughout. And that is now a very popular graduate elective. Last time I had over 370 students enrolled in that course. And I really am finding it tough to offer it. So that is my short journey. So what I do is that I put AI, ML, along with engineering together to create solutions. And I have been a hacker, a hardware hacker ever since my undergraduate days. So I also do a lot of IoT and my group does IoT. I do, of course, AI, ML. I do hardcore engineering. You have seen my labs. My labs look very different from the AI, ML labs. I work for a lot of companies over the last 15, 14 years. I have been able to generate over $15 million of funding. I work with GE, General Electric, Boeing, General Motors, Sandvik, DMG Mori, Zeiss, Tata Group, GSW Group, Reliance, L&T, Godrej, Bharat Forge, and Gems and Jewelry Skills Council of India. There are many other companies which I work with. I'm not putting the names, they're just on and on, but certainly I've not put names of any companies which I'll be talking about today as case studies, except GGSCI, which is a government organization, Gems and Jewelry Skill Council of India. It should be JG, not GJ, but anyway. Apart from that, I work very closely with many ministries. I am a government employee, central government employee. I work with my ministry, of course, Ministry of Education, but I work with Ministry of Science and Technology. The current DST head is, of course, another colleague of ours from IIT Bombay. I work with the Defense Ministry, MITI, Department of Heavy Industries, Textile, work with BIS, National Labs, Defense Labs. So I have a very large portfolio of things which I do. So what I'm trying to say is that there is always something which I know about something. So you bring me a problem and I have probably done something. As much as bovine tuberculosis in UK to looking at breeding of horses for the Indian Army. So I have looked at a very large, and you may ask, what in the world are you doing? But I have done everything in some or the other, form. So that makes it very unique. Of course, you have seen this. I'll skip this. This was one of the facilities which you saw. This was the other facility which you saw, but this is what you can see from that, the microscopy facility. But what you did not see was this, a machining cell which is a very advanced machining cell, fully instrumented. Everything which we do has a simulation part of it, and of course the experimental part of it and the data part of it. I also do a lot of composites. I could not show you composite facilities, but I did show you some of the composites which we make. And this is again to show you the same thing. We do modeling, actual manufacturing, and then characterization. So coming to the real elephant in the room, the digitalization and digital transformation. So what if you look at AI? AI is a very old word. It's older than any one of us. More than 70 years back, the term artificial intelligence was coined, and it has been there for ages. People thought finally that it will only be science fictions which will have AI. But about 12, 13 years back, things changed, 14 years back. And that's when really AI started becoming very powerful and started challenging, the natural intelligence. The artificial intelligence is now becoming a challenger for natural intelligence. I teach lots of courses to industries. I have taught more than 900 industry personnels in artificial intelligence and applied machine learning. So AI is a much bigger term. Machine learning becomes a smaller term, where the idea is that machine can learn from data. So if you have data, the machine should be able to learn. And that is where I work. And that's where data becomes very important. And this is just one of the displays. You've seen some of these devices. We make our own IoT devices, but we can also connect with any PLC, any controller, pretty much anything which you have, which has data, we can extract that data. By hook or crook, we have a library, fine, but otherwise we can just always instrument it, and we can, as long as it is ethically acceptable for your supplier, because most of these companies have machines which have their OEMs, and the OEM says, okay, you can do anything which you want, we can extract data. This is just to show you that we need data, so we feed on data. But data is not enough. It's like fuel. But you can't burn fuel unless you have oxygen. So you need two things for things to burn. Data is just one fuel. So then you use data and you come up with AI. These are some of the displays which we had at a recent industry. So what really is data? And I'll talk about that fuel part right now, but later I'll talk about the oxygen. So data has many aspects, but most of the data which I work with this, which is the industrial data, is data which may fall in the category of big data. It's large volumes of data. For instance, with Air Force, we are working with 4 petabytes of data. Now, for 4 petabytes of data to be read by your GPUs and written back, just for one epoch, just imagine how long will it take. So that's a completely different ball game. Just for one platform of theirs, they have 4 petabytes of data. So volumes could be huge. But other than volumes, they also are real-time data. It's a data which is flowing. You're continuously having, so there's a data velocity associated with it. So live streaming data. Your machine is running, it's continuously sending data. You have to make a split-second decision. You can't be taking gigabyte per second and having your GPUs just go crazy. So you have to be very selective. You have to be having algorithms which do the reduction of data to actionable data. Then, of course, you have a huge variety. You have text, data, tables, images, video, audio, complex structures. And once you have such large data with high velocity and variety, you certainly will have a lot of veracity. I work with industries and they claim great data, and suddenly we see models are going crazy, only to realize that some of the data is wrong because the sensor went wrong, or the connectivity went down, or the person who was copying, sometimes they are just copying an Excel sheet. I can't believe, but we are still doing that, and they copied it in the wrong column. So you have what we call as veracity. The data has errors, uncertainty, incomplete data, missing data, ambiguous data. And all of this is what we have to take together and make sense to come up with solutions. So you need to be able to have a real problem solved, not a fictitious problem. An industry should say, okay, my productivity has to go up, my scrap rate has to go down. There is no ambiguity about it. 6 years, my scrap rate has never gone below 6%. Can you get it below 4%? Now, if you can get that done, you are in for life almost, You can expect that they will have multiple problems coming to you. But this has to be the thing. So now what we do, majority of the cases, is what we call as supervised learning. What is supervised learning? And it's important to understand this aspect. A lot of work has been going into supervised learning. What is supervised learning? It's where you have a relation between input and output. You do something, you get something out. Is it good or bad? So what should you do so that you get the right stuff out? So this is where you have an input and an output. Inputs are called sometimes predictors, dependent variables, features, factors. There are many names to it. And outputs are called responses or the dependent variables. So imagine you're producing something, you're having a scrap rate. What percentage of scrap you're having is an output, and inputs are all the process parameters which you had. Now this is where supervised learning comes into play. You take past data, you take inputs and outputs, you train your model, and the machine learning goes through a training process, validation process, and then testing process, and then you are able to have a model which can predict some kind of a regression or a classification, and you are able to predict when you get new input, without having an output, you can predict the output. But then there comes another kind of a model where you don't have an output. What if you only have inputs, no outputs? Imagine I ask you to search for quantum entanglement. You know quantum entanglement. You can go to Google and search for quantum entanglement. But what if you don't know some kind of a abelian cyclic group? You've never heard of it. How will you go and search for it? So there are two kinds of ignorances we have. The first kind of ignorance is of things which we know we don't know. So I know I don't know quantum entanglement. Fine, no big deal. Go Google it, go to a physics professor, find it out. But then comes the next kind of ignorance in which we don't know what we don't know. You don't know what you don't know, so how will you search for what you don't know? Because you don't know about it. So the terms which you never know, you will never be able to search for it. You won't be able to seek answers for it. Maybe there is the most delicious dish which you would love. You've never tasted. How will you ever get to know that? And that's when the unsupervised learning comes. It creates that awareness of things which you don't know you don't know. You have only inputs, you have no outputs. But can you see patterns in it, which you never even asked a question for? So that's where you do change point detection, cluster analysis. There are a whole lot of algorithms. And big data becomes and goes into the area of data discovery, knowledge discovery. You start discovering things which you never even... So discovery is somewhere where you don't really know. You suddenly discover something new. Whereas you are working for a specific kind of an invention and you invent something which will solve your problem. So right side becomes, in a sense, invention, and left side becomes a discovery. So we do both the things. But most of the people come to us because they know what they want, which means they have an input and output, and they want an output to become better based on the input. But in the process, sometimes they realize, oops, there are many things which they never even questioned. Those questions can be answered, but they did not even know which questions to ask. And of course, then there are many other aspects, reinforcement learning and same as supervised learning. I heard a lot of terms on accuracy, and this is few slides I just put them because I thought it may be a good idea to kind of sensitize you that accuracy may not be the best measure. What is accuracy? In a classification problem, you have true positive plus true negative divided by the entire sum is your accuracy. So imagine you are trying to predict something and you say, I have a 99.9% accurate model. Is it a great model? 99.9, of course. It sounds very great, right? Why? Because our scheme of 99.9 is, oh, I never scored that many marks in my grade. 99.9 suddenly makes you feel, so you have a benchmark which you start doing things with. However, that could be a horrible model depending upon the cost of errors. So a 99.9% accuracy can be excellent, good, mediocre, poor, or terrible depending upon the problem. So if, for instance, you are taking your friends for a birthday party and the review says this is a 99.9%, it says that this is a great restaurant, 99.9% accuracy. You say, well, no problem. Once I live 1,000 years, maybe once I will take my friends to a wrong restaurant if I have this kind of accuracy, right? So I'm fine. I'll go to a restaurant which is 99.9. That's fabulous. But now I'm walking out of this, and suddenly I realize a live wire starts touching this doorknob. I'm not sure if it's live or not. You call the electrical people. They say most of the wires which are falling in VMCC are not live. Don't worry. I'm 99.9% sure it's not live. Please touch it and go ahead. You will think twice. 99.9% accurate that this is not a live wire means 0.1% I may just get electrocuted, 440 volts, maybe 1100 volts. So suddenly you realize the cost of your misclassification is something which is not possible by an AI person. It has to be done by the person in business. The business has to tell you. The domain knowledge has to tell you, is this acceptable risk or not? So that's when accuracy is not a very good idea. But there is another reason why accuracy is not a very good idea. And in my area where I work, most of my people whom I'm working, most of my clients or my collaborators, they come to me for defect reduction. Now they have one defect in 1,000. They want to make it one defect in 10,000. The moment I hear one defect in 1,000, I'm like, oh wow, no problem. I'll give you a model which will predict whether it is defective or not with 99.9% accuracy. Why? Because they anyway have one defect in 1,000. I'll always say no defect, no defect, no defect, no defect. Only one. Once I'll be wrong in 1,000. 99.9% I'll be right. 999 right. So when the data is highly skewed, when your defects versus no defects are not equal in proportion. If you had 50% defective parts, 50% good parts, then this is a good model. But if you have only one defective part in 1,000, then again accuracy is not a great idea. So there are many reasons you don't want to go on to accuracy. So next time when someone sells you a AI model, please come to IIT Bombay and do a project with us. We'll get you the right stuff, because they are probably cheating you by selling you a 99.9% accurate model. So what you really need to do is they have to look at something known as a recall and precision. And if you ask these two questions to those guys, that what is your recall, what is your precision, the moment you ask these two questions, the numbers will be so bad that you'll get to know that this is not where you need to be. I don't want to go into more details. There are more interesting stories with this. Then there is another thing known as F-score, which essentially combines both recall and precision. So if someone asks you what is the accuracy, this is the accuracy, ask what is your F measure or F score of that. And that will tell you if it's not good, if it's not very close to 1, then you are not doing good. Now I'll quickly take 3 case studies, or maybe 4 case studies. I've added one more. I'm not naming the industries, though they are kind of okay with we have published some work without naming them in a pseudo format, but I still don't want to be. So this is data which is already published, but I don't want to still name the industry because they didn't want to be named even in the publication. So this is a leading induction motor manufacturer in India, and they are very forward looking. They want to create a quality control division based on AI, which can predict if their induction motor has one extra field winding. If accidentally you add one extra field winding, they should be able to detect, or one less field winding, they should be able to detect. So they want that high level of precision in their QC. And they said, can it be done? Now he said, we certainly can, provided the data is good enough. So everything depends on data. So we work very closely with them, and we have developed lots of technologies and lots of algorithms which are fully tuned just for their industry. We are giving everything to them as per our IP clauses and other things. So they have given us a captive project. They are funding us. We have been visiting their sites. We have been working with their R&D center. And now we are developing algorithms which we have demonstrated. We will eventually provide them the entire algorithm with the weights. The algorithm will stay with us and we can use it for anything else, but we can't use the weights because those weights have been trained on their data. However, we have created more weights on our data. We have generated data, and this is the data created by our IoT devices in our center. So we have not really used their data for this publications. Now, this is where I can pick up the phone anytime and call this guy that I need to go to your industry. I need to talk to someone in your industry. So they have a manufacturing facility at 2 locations. They have an R&D facility at 1 location, and then they have a IT facility where all the data is stored and their SQL data and other databases. And I'm able to talk to all of them by talking to this guy anytime. And anyone in my group can call him up, and he feels he can call me up anytime as well. And this is something which has been working fabulously. We are about 3 more months, we'll complete this project. We've already done a lot of stuff. This is case study number 2. This is with a company in US, which also happens to have an Indian presence. Again, I can't use their name. This project is over. They are extremely super happy with our work. What we were doing here was that we were predicting green powder compaction defects. So they're making inserts, and these are made by powder pressing, then sintering, blah, blah, blah. There's a very long process. We were only involved in the first part where they do pressing to make these inserts, and they were having about 20% rejections. They're very, very quality conscious. So they used to have 20% rejections. And we worked very closely with them to see what are all the data. What we realized, they have more than 800 variables. They have more than 800 variables. They have so many variables that you cannot really train a model on that. But since we know domain knowledge, we know metallurgical, powder metallurgy and other aspects, we were able to reduce them to 40. Then they had more than 200 different, more than 1,000 different classes. Defect A, defect B, defect C, defect 3. They have 1,000 plus different kinds of defects. We realized they have only 4 defects which has more than 95% of the numbers. We said we don't want 1,000 defects, we just want 5 defects. Defect 1, defect 2, defect 3, defect 4. 95% of the defects are taken care of. And defect 5, which says others. We just need 5 labels. We don't want to have 1,000 labels being predicted. And they were like, oh wow, such a simple thing. We should have thought of this. But all of these things put together, we were able to solve and develop the entire code, show them, and then work very closely with their team to get it deployed by them in their Azure servers. They deployed everything, and the process was so great. In the process, they learned what we had done, because otherwise, had we deployed, it would have been a lot of resource for us and they would have not learned. This is a company which is in US, and they are super happy with us, and they are now back for a second phase. This is the third company, and again, I won't give you the name. This is a company which sponsored multiple projects with us. This is a German company. This is an AI company, by the way. This works in the area of Industry 4.0. Bunch of brilliant computer science people from various places, including India. They could not solve the problem because it's a manufacturing problem. They could not solve low-pressure die casting defects which were happening in an aluminum alloy wheels. They took up a problem. They could not solve it. They finally came to me. And since I understand casting, low-pressure die casting, high-pressure die casting, aluminum metallurgy, formation of gas versus shrinkage porosity, how the heat transfer, mass transfer, momentum transfer, phase transformation happens. And of course, I understand data science, AI. I have been working in industry. I have worked myself in industry. I could come up with a very simplified model of AI for them to be able to implement for their clients and get their defects rate from 8% to 6%. Now, it may sound just 2%, but trust me, as you start going down to 0, every single percentage is a very, very tough thing. Now, they were very happy. They did an MTech project. This is a part of the MTech thesis. It's there in the library here. You can look at it. Now they have a problem again. They have a client where they did something which we had told them, and the defect rates have gone up. Why? Because it's a different alloy system. It's a different wheel. It's a complete different system. They kept using what we had told them, never built a domain knowledge. They came running back to us. We need your help again, because it's a different wheel. It's a different alloy system. It's a slightly different process. And we said, well, we'll be happy to do this. And they are an AI company who are the front end, who provide these services to these manufacturers. And we are, in a sense, becoming their partners. Finally, last, which is the fourth, which is from GGSCI, Gems and Jewelry Skill Council of India, funded by Ministry of Information and Technology. This is where we were trying to predict demand for jewelry sales. So this was an AI jewelry demand forecasting. Now, jewelry sales are very strange because they're not always happening every single day at the same pace. Unlike petrol, which you buy pretty much every day at the same pace. You know, weekends are a little different, but otherwise petrol is a very uniformly sold thing, except unless, of course, you get to know, or tomorrow the cost will go up, so you'll have a long queue for petrol. So what happens is that there are lots of things. What kind of jewelry? Rings, necklace, earrings, bracelets, chains, pendants. What kind of alloy? Yellow alloy, white alloy, platinum, silver, which caratage, 22, 18, 11, 14, 10. What weight? All these things. So there are some 16 kinds of variables. These variables can be put into the jewelry variable, external forces, the customer, and the shop. External forces could be the drop in rupee or dollar equation, drop in gold price, change in stock market. These are external factors. Your sales will go up because of that. Of course, the jewelry is, of course, which jewelry you buy. So we were able to put all of these together. We worked with 7 industries, which were brought together by the Gems and Jewelry Skill Council. And we were finally able to develop a model which can predict very precisely the actual thing. So we had 3 years of data. We took 2 years of data to model it, to train our models. Third year, we predicted and saw how good is the prediction as compared to the actual value. And we are able to very precisely predict this. Now, this is a collaboration between industry, academia, and the government of India. So government has paid half of the money. Half of the money comes from industry. And what do they get? they get to be the first one, the industry gets to be the first one to use this model, but the government wants this model to be available openly to everyone. So Gems and Jewelry Skill Council of India is going to be the custodian of this model. They will take this model and they will deploy it and will make it available to all the jewelers who are jewelry retailers who are a part of this. So this is to show you another aspect. All of these things have primarily two things in common. One is that the data comes from the real world and the data comes from the simulation world, and it all goes to finally the intelligence, the AI. And that's how we build digital twin. You have seen this in the past. I'm just showing you there are a lot of other things which we do. We do a lot of video analytics, AI-based assist, specifically on domain knowledges. So you could have specific domains on which you could have a chat bot. We have, of course, our IoT devices which we take the data with. So last thing which I want to quickly show is that what should be the industry academia model, and there is no one single model. And Dean R&D will be talking more about it, but I thought this could be one slide which I had been using in the past. We have three basic ways of interacting, and you can think where you are fitting in. One could be exploratory projects. These are 3+ years projects. These are usually driven by PhD students, and these PhD students publish papers, and the funding can sometimes come by industry, and some industries are ready to fund these, and there are many industries who have funded me for this. But there are more often industry consortia or government and industry collaboration. Government gives money, provided industry is ready to match or give maybe 20%, 30%, depending upon what the projects are. So this is one major area, and you all should really look at that and explore that to collaborate with us, because government gives a large money. However, you publish, you are not able to patent. Second is innovation projects where only industry funds. We can file patents. We may have our MTech students work on it or our RAs work on it. If it's very secretive, you don't even want a thesis to come out of it, this will be done by research associates. I have almost 100+ research associates working in my center. This is 1 year, and then you could have developmental projects, 6 months, where you, of course, only have a research associate work. These are technologies which we develop, no patents filed. You use this technology, it's very specific technology for you. And again, the funding only comes from industry. So with that, I will stop and I'll tell you what is the secret for successful industrial project. Of course, first is technical. You need to have a very clear problem definition. Don't keep changing the goalpost. You need to have a very, very clear focus. Faculty are more likely to change the goalpost, by the way. We are exploratory minds, we just keep thinking this, what about this, what about this? But you need to be very focused, and many of us have worked. We are 800+ in IIT Bombay. At least half of them have actually worked in industry at different levels. So we are very much focused towards industry. It's not that we are not the 25-year-old back, when IITs were all academic. We are now very close to industry. Clear problem definition is very important. Availability of data, you need to be having the data and should be willing to share the data. We can certainly sign all the non-disclosure agreements. Your data will be safe with us. You don't have to worry about it. Combination of domain knowledge and AI is something which is must. Any industrial problem you cannot solve unless you have domain knowledge. Be it industrial problem, be it the medical problem, be it the problem in finance, you need domain knowledge. These are three technical aspects. Administrative factors are funding, of course, and there are many ways of funding. As I said, you could have industry, academia, government collaboration, or you could just be funding yourself. IP sharing can be worked out. Our dean's office has multiple models depending upon what you need. We have worked with another US company where they wanted all the IP. We said, we don't even know what we'll produce, but if you want everything, you'll have to pay this large amount. And then they realized, oops, if upfront I have to pay this, they said, no, don't worry. Once the IP will be created, we can renegotiate. So you could have IP, don't worry, there is a model for everything which you may want. And finally, the implementation. And this is, I think, one of the key importance, that how is a model successful or how is a project successful is how it is finally implemented. It should not be a push from my side. It should be actually a pull from your side. Someone should be ready to take it and should be ready to take it every single day. And that is where Amit had also mentioned, and I'll re-mention it, you need a single point contact, an industry champion. Every single project which I've talked to you about, I had one guy in industry whom I could pick the phone up and call anytime. And he could call me anytime. We have any doubts, I don't have to write a formal mail, copy his boss, copy my dean or anything, nothing. I just pick the phone up, I call him. We just sort out everything. Once everything is sorted, if we have to formalize it, we formally write a email to just formalize what we have already done. You don't want to write mails back and forth. So you need an industry champion. So I think that is one of the key aspects. So if you have a clear problem, You are ready to share your data. That's when you need an industry champion. And once you have these things, that is the way to succeed. So that's all. Thank you very much.